In the study of biostratigraphy, we sometimes use graph theory. Graph theory, first of all, does not involve the x and y axis and some graph. In the school, we have studied x and y axis and some graph. In graph theory, we don't cover, neither we cover x, y and the z axis and some three-dimensional surface or curve is also not covered. What is a graph? It consists of a set of vertices or nodes and the edges. Imagine there are 4 points or nodes or vertices V1, V2, V3 and V4. In some standard form, instead of Vi we write as Ni, that means instead of V1 we write as N1, V2 is written as N2, etc. Anyway, here we continue with Vi, and when we see biostratigraphy, instead of Vi or Ni, something else can be written. Now, these vertices in the graph, some of them can be connected and maybe not all the vertices are connected. The lines that join them are called edges. So, I can write this as E1 and this as E2. So, the V1, V3 is joined by E1 edge and V1, V2 is joined by the E2 edge. In graph theory, we study the vertices or nodes and their connection. Now, such graph can be presented in a matrix form. Let us try to understand. In this case, we have got 4 vertices. So, I can write V1, V2, V3 and V4, V1, V2, V3 and V4. We are going to construct a matrix that will represent the graph. This G will be represented by a matrix M. First observation, is the V1 vertex connected with itself? Now, this is a question, you can stop the video and think and then move forward. The answer is, as per this graph, V1 is not connected to itself. I will explain it. And if the nodes or vertices are not connected, I will write 0, which means not connected, and I will write 1 if they are. We say V1 is not connected to V1, so we write here 0. Is V1 connected to V2? The answer is yes, so here is 1. Is V1 connected to V3? Yes, so the answer is 1. Is V1 connected with V4? The answer is no, so it is 0. Next, is V2 connected with V1? The answer is yes. Is V2 connected to itself? For the time being, I am saying no, so it is 0. Is V2 connected to V3? No, so it is 0. Is V2 connected to V4? The answer is no, so it is 0. Now, we take V3. V3 is connected with only V1, so it is 1, and for rest of them it is all zeros. V4 is not connected with anyone, so I will put all zeros. So, this I can call as Vi cross Vi square matrix. What is a square matrix? A matrix where the number of rows and columns are the same. So, here the number of rows equal to the number of columns is equal to 4, and this is the way we represent the connectivity. The graph theory has a very wide application in mathematics, in electrical engineering, in structural geology, groundwater flow, and we will also see in biostratigraphy. And it can be considered as a versatile means of studying the large data set, their connectivity, are they connected or not, that is being presented. Now, this matrix that we constructed, you can see, is a new kind of matrix which probably we have not seen earlier. So, this matrix properties will be different from the matrix property that you have studied. Let us try to understand. When I said V1 is not connected with V1, V2 is not connected to V2, V3 is not connected to V3 and V4 is not connected to V4, and that is reflected by these diagonal elements. All the elements are giving 0. What does it mean? Imagine V1 is a mobile phone and is connected to V2, another mobile phone. So, I am giving example of mobile phone. In fact, landline phones will also serve the purpose. Now, the question is, from V1, from this phone, can I call myself? The answer is no. With V2 phone, can I call myself? The answer is no. Through technological progress, one can make a phone where I will be speaking and I will be hearing, but that is useless, because anyway I can speak to myself. Therefore, in such a case, V1 is not connected with V1, V2 is not connected with V2, and V1, V2 are interconnected. So, in this case, the matrix representation will be, and again you see these diagonal elements are 0. So, this is the physical meaning of Vi not connected Vi. Now, we are going to see another example where V1 and V2 are connected to themselves also. For example, V1, V2 as the email addresses. From V1 email address I can send an email to V2, from V2 email address I can send an email to V1. I can send mail to myself, so I am connected to myself. So far the email address is concerned, same with V2, and in such cases we present the connection by these loops. When Vi is connected to Vi, Vi will be shown by a loop. So, here what will be the matrix presentation? All the elements 1, and in such a situation it also immediately indicates all the elements are in the matrix are 1, that means all the nodes are interconnected. If I find a Vi into Vi matrix where all the elements are zeros, it can be 3 into 3, 4 into 4 or 97 into 97. This means that none of the vertices are connected to each other. We will now take another example to increase our concept V1, V2 and V3. If I draw lines like this, we say V1 and V2 are connected to each other, we say V2 and V1 are connected to each other, we say V3 and V2 are connected to each other, and inversely V2 and V3 are connected to each other. If I pose a question, is V1 connected to V3 as per this graph? What do you think about it? Pause the video, think and then move ahead. I hope you pause the video. Now, here is the answer. V1 is not connected to V3. Whenever we are saying connection, we mean direct connection. So, the indirect connection is not considered as connection, and let us try to understand it. Consider V1, V2 and V3 in the above case are the 3 friends, are human beings, and the age represents friendship. So, we can say that V1, V2 are friends and V2, V3 are friends. Now, a friend's friend may not be my friend. In this case, as per this graph, in this special case, a friend's friend, V1's friend, V2, V2's friend, V3, and V1 and V3 are not friend to each other. So, here V1, V3 are not friends, and if they were friends, then what would have been the presentation? The presentation would have been, this is a case when everyone is everyone else's friend. My friend's friend is also my friend, or if I increase the number of vertices V1, V2, V3, V4, V1 is V2's friend, V2 is V3's friend, V3 is V4's friend, and in case the situation is such that V1 is also V4's friend, then I will join that by another age. Okay. Now, Once we constructed the matrices, I have used 0 and 1, a binary code, and which has an advantage of using in computers. This 0 and 1 what indicates is only the direct connectivity is presented. Are they connected or not connected directly is presented. No other thing is presented in the matrix. And the matrix is independent of length or geometry of edge. For example, here is a bulb and here is a plug, and they are connected by a wire. Now, this wire can be oriented like this, plug and there is a bulb, or it can be oriented like that. So, you can see the edge geometry, whether it is straight line or curved line, and the length do not matter in case of the graph theory and in case of the presentation in the matrix. This is an obvious and important point. Now, once we have studied edges, we have seen two possibilities. Edges can be real. An example is that there is a plug and then there is a bulb and then there is a wire. Example is a wire. It has a physical presence. Or edges can be virtual. That means, let us say, friendship. Friends are not connected by any wire. An example of virtual edge can be the chemical bond. So, these chemical bonds, they do not exist in reality. We cannot think a string is connecting carbon and hydrogen. In fact, any organic compound can be represented by chemical bonds, and these bonds themselves are examples of edges. So, if in terms of vertices we want to present, it can be V1, V2, V3, V4 and V5. Then magnetic attraction and repulsion. This also can be considered as the edges, but when we say that the 2 points are attracted towards each other, there is no string or line actually present in between them. Same point when they are repelled. We want to see another way of presentation in terms of matrix. We can write the vertices V1, V2, V3 and V4, and here we can write E1 and E2. All the edges are written here, all the vertices are written here. Now, if they are connected, I will write 1, if they are not connected, I will write 0. V1 is connected with E1, so it is 1. V1 is connected with E2, so it is 1 here. Vi multiplied by Ei matrix. Now, note that when it is Vi multiplied by Vi, we have called it as a square matrix, but Vi into Ei matrix may or may not be a square matrix. For example, here we have got 1, 2, 3 and 4 rows and only 2 columns. So, here it has got 4 rows and 2 columns, and therefore, is not a square matrix. But if I draw any other edge, say I decide this is an edge and then I add one more. So, we have got not just E1, E2, but E3 and E4, then it becomes 4 rows and 4 columns. The number of edges can be more than the number of vertices. As an example, if I join this and if I join that, we have got now 1, 2, 3, 4, 5 and 6 edges and 4 vertices. So, in this case, the number of edges can be more than the number of vertices. Number of edges can be more than number of vertices. Note that this matrix is a symmetric matrix. You can see that these two elements are same. These two elements V3 V1 and V3 V1 obviously are the same. and these two elements V4 is not connected with V1, V4 is not connected with V1 obviously are the same. Then V3 and V2 and V2 and V3, these two elements have to be the same, V4 and V2 and V4 and V2, here they are zeros, but both of them can be 1. It is not possible that here this is 1 and that is 0, not possible. Look at the diagram from where we started and you can think, and here this is 0, V4, V3, and you have got V3, V4, they are the same. And we can write that number of edges can be equal to the number of vertices, or the number of edges can be less than the number of vertices. Three possibilities are there. Graphs I have shown, those can be considered as unoriented graphs. What are those? Where we have V1 and V2 and as the vertices and they are connected and there is no directional meaning. I will explain it more clearly when I say that there is a possibility of an oriented graph. What is that? Say we have got vertices V1, V2 and V3 and there is some directional sense. I have given by arrow, I have given V1, V2 and I have written V3, V2. That means something is flowing from V1 towards V2 and something is flowing from V3 towards V2. This means and the flow is not opposite way. For example, the above graph does not mean is not happening and is also not happening. Where vehicles can move from only V1 towards V2, human beings have decided, or consider an inclined pipe and water is flowing. So, from this vertex V2 towards vertex V1 there is one way flow, unless we push the fluid from this side, that is not there, free flow, natural flow is considered. So, water flow or fluid flow can be an example. Such graphs are known as oriented graphs, also known as digraphs or directional graphs. This is the time axis and a species progression with time is shown, and after here the speciation happens, new species is produced, and therefore this line breaks into two parts. So, I can put a vertex V1, this as vertex V2, this as vertex V3 and this as vertex V4, and there is an arrow V1 towards V2, V2 towards V3, V2 towards V4. We cannot go back in time, so V2 towards V1 is not possible. So, I have given a case of evolution of life as an example. To give more examples of the digraph, one is fluid flow I have said, another is one way street, the evolution of life. The other example can be flow of current, electric current, and in this context we can think of flow of electron, heat flow. These can be considered as examples of digraphs or directional graphs or directed graphs. Now, we are going to see how the digraphs are presented in a matrix format. Now, to present this digraph, we will create a Vi into Vi matrix, and V1 is not connected with V1, so it is 0. Here we will use +1, 0 and -1. 0 use is obvious when they are not connected. These two +1 and -1 I am going to explain. V1 towards V2 is a flow, so it is +1, V1 towards V3 no flow, V1 towards V4 no flow. Now I take V2, V2 towards V1 there is no flow, but V1 to V2 was a flow, so I will put a -1. So what has happened, whenever I am writing V1, V2 etc. here, V1, V2 etc. here, my preferred way of writing is, this is from and this is to, like flow from V1 to V1 I have to write down 1, -1 or 0, from V1 to V2, from V1 to etc., from V2 to V1, from V2 to V2. So, this column everything is like from, and in this row whatever is written is everything to or towards. In this sense, this matrix has been constructed. It is again a square matrix. Why? Because the number of rows equal to the number of columns, and it is equal to 4 in this case. Okay. Now, we want to see the property of this matrix. We can call this matrix as the skew symmetric matrix, or we can call it as the anti-symmetric matrix. Why? If V1 to V2 is 1, then V2 to V1 has to be -1. You can see a sign change has happened. If V3 to V2 is -1, then V2 to V3 is +1, we can note a sign change. If V4 to V2 is 1, then V2 to V4 is -1, we are observing sign change. So, here by putting this double sided arrow, we indicate that there is a sign change involved. We have seen Vi into Vi matrix. Commonly, we do not try Vi into Ei matrix. So, we have seen unoriented graph and oriented graph, and in the oriented graph or the digraphs, we have seen use of +1, -1 and 0. Now, we are going to use another concept, the weight in digraph, the concept of weight. Say V1, V2, V3 and V4, and some flows are taking place like this, and we assign a number from V1 to V2, 8 unit of flow is happening, from V2 to V3 5 unit of flow is happening, and from V2 to V4 3 unit of flow is happening. Now, these numbers 8, 5, 3 are called the weights of respective edges. Volume of fluid that is flowing, or it can be volume of fluid per unit time. It can be some unit of current flow, or it can be the number of persons walking in one way street, any number which is having a directional meaning. Weight of fluid flowing per unit time. Now, we are going to have a matrix presentation, and we are going to utilize the weight will be used in the matrix. Let us see how it is done. V1, V2, V3 and V4, and here I write V1, V2, V3 and V4. Now, there is no loop. V1 to V1 flow is 0, V1 to V2 is 8 unit flowing, V1 to V3 there is no direct flow, so it is 0, V1 to V4 there is no direct flow, so it is 0, V2 towards V1 it will be -8. Now, let us try to understand the property of this matrix. What I am going to explain for this 4 into 4 matrix as a property will also be holding true when it is very large number of nodes involved, let us say 3,522 multiplied by 3,522. So, the advantage of learning property with small matrix is that we understand it and then we can implement for matrix with so many vertices if required. Okay. So, in that way we can handle large data set also. In the graph theory, we are not producing new data set, rather we are representing the data set. Out of curiosity, you can add up all the elements in this matrix. What will happen? First of all, there are certain 0 terms, so the sum of them will be 0. Then it is an anti-symmetric matrix. If somewhere we have added plus 3, elsewhere we have given minus 3. So, all of them will be summed up to 0. So, the grand sum will be 0. Check it out. 0 plus 8 plus 0 plus 0 plus minus 8 plus 0 plus 5 plus 3 plus 0 minus 5 plus 0 plus 0 plus 0 minus 3 plus 0 plus 0 turns out to be 0. I am adding up all the elements in this row and the sum turns out to be 8. The same thing we are now going to do in terms of the columns. All these elements are added up and we get minus 8. Now, we are going to focus on these numbers that we have added up. If the V1 sum of all the row elements is 8, the V1 sum of all the elements is minus 8. If the V2 sum of all the elements is 0, same sum has been obtained here as a V2 column sum. If the V3 row sum is equal to minus 5, then the V3 column sum is 5, and if the V4 row sum is minus 3, the V4 column sum is 3. If this sum is equal to plus x for say Vm, then this column sum has to be minus x, and if any sum here has come as 0, the sum there has also come as 0 for let us say Vn. Now, this is not anything unusual or magical. For example, when we are summing the V1, all the elements V1, V2, V3 and V4, and here it was V1, V2, V3 and V4. This is the from side and this is the to side. So, from V1 to V1, from V1 to V2, from V1 to V3 and from V1 to V4. So, this means if I sum up all the V1 elements, it means from V1 to elsewhere. This is the meaning. If I sum all the rows here, this sum will indicate from V2 to elsewhere. Physical meaning of summing up. And what about this sum up? From V1 how much comes to V1, from V2 how much comes to V1, from V3 how much comes to V1 and from V4 how much comes to V1. So, here it means from different nodes how much comes to V1. So, you can see this is all about income in V1 and this is about outgoing, how much is going out from V1. So, this sum will indicate how much total is coming to V2, this sum will indicate how much total is coming to V3 and this sum indicates how much total is coming to V4. So, what I wrote here is a physical meaning of this summing up. Now, back to the previous slide. Here if we add up all the elements, how much turns out? Turns out to be 0, and here if all the elements are summed up, it turns out to be 0. That's another important and obvious point. You can think physical meaning, you will be finding out very easily. A second observation is that there are certain vertices where the column sum is 0 and the same vertices here where the column sum but the row sum is equal to 0. What is the physical meaning of this V2? What is so special in V2? I am writing the question here. What is so special in V2 vertex? To do that, again have a look at the graph and think about it. Stop the video for a while, try to find out the answer and then again start the video.